Hello, in this section we will look at the basic classes of function. Before we start, I would like to point out that we also have an elementary function, like cup functions, couple of graphs, around 10 graphs, and these were covered in section 1.1. That means please make sure that you are confident with elementary graphs before taking calculus. Okay, because it will be really important to be confident with some elementary graphs like x squared, x cubed, 1 over x, and so on. Please visit section 1.1. Okay, but in this video, we will just look almost at the same things, just the basic functions. We do have two classes of function. We have algebraic functions and we have transcendental function. Algebraic are power function, polynomials, rational function. All of the functions that we can look at them through the algebraic operations: addition, subtraction, multiplication, division, so on. Transcendental functions are a little bit different. We still can do algebraic operations on these functions, exponential, logarithmic, trigonometric, that's the transcendental, but they are not defined through the algebraic operations. Okay, and then we'll try to graph piecewise defined function. Okay, that's the plan. Let's see. Let's start. I hope we can start, yes, with a definition of the function. That means function f from a set D domain to the set Y range is a rule that assigns each element x from the domain to one unique element y from the range. Okay? That means we write this. D is domain, y is range. And again, I have these basic functions listed for you. Okay, now polynomials. In polynomials, I would say that's the easiest function. It's one of the easiest functions. That's in polynomial is a sum or the difference, but we know that we call difference the addition of a negative numbers. That means it's a sum of multiples of the power function, and power function is defined like this. X to the power of n. My screen is, okay, x to the power of n. That's the power function. Exponent n has to be positive integer or 0 sometimes, okay? But definitely n is a positive integer, and I hope we know what is integer, positive integer, which is called natural numbers, okay? Basically is 1, 2, 3, and so on, okay? Positive integers. Okay, and then the degree of the polynomial function is always, we will say always the highest degree in the expression, in the formula. Okay? That's when we can see this equation, this formula. P of x equals to a sub n x to the power of n plus a sub n minus 1 x to the power of n minus 1, and so on. A sub 1 x to the power of 1 plus a sub 0, which is a constant. That means all of the a's, all of the numbers next to n is called coefficient. Right? Leading coefficient will be the coefficient which sits next to the highest power. And usually we can say that leading coefficient is supposed to be non-zero number, because when we eliminate that, if this will be 0, then the degree is not n, okay? Because we will lose that term. That's the reason that if we call that this polynomial is degree n, we need a sub n to be different than 0. Okay. And the good thing is, for the polynomial functions, domain is all of the real numbers. All of the real numbers. We have no problem to substitute any x, and we will always get the real output. Okay? And that's, for instance, the example of the polynomial function. Nice, smooth, wavy curve. Okay? And what we need to know, yes, how to actually draw this graph. That's one of the important things, yes, will be like how to get, maybe from the graph, we're supposed to get the formula, but let's just get the formula and get the graph. Before we do the big one, let's look at the monomials, the individual power functions, and just x to the power of n. It's just called monomials. And then we can see x to the power of 1 is just the linear function. And also, I will recommend to check section 1.2 for the linear function and all of the nice examples. Okay, now x squared, yes, that's also one of the elementary functions. It's parabola, yeah, with the x-intercept 0. X cube, also one of the elementary function, looks like this. And now, right, if we increase the degree, yes, degree that the exponent is getting like higher and higher, and we only looking at the even numbers, like x to the power of 2, x to the power of 4, x to the power of 6, 8, and so on. All of these monomials, all of these functions will look like parabola. We can see x squared, x to the power of 4. However, if the degree is getting higher, the graph is getting flatter around the 0, around the x-intercept. Okay, that's mean, please, yes, make sure that if this will be x to the power of 6, it will be even more flatter. And the same, x cubed supposed to be like the template, like the function that we know, elementary function, how this looks like. And now x to the power of the next odd number will be x to the power of 5, looks almost like an x cube, but it's flatter around the origin. X to the power of 7, it will be even more flatter. Okay? That's how we can know how to draw these functions. Okay, that's when we know domain is no problem. Domain is all of the numbers. Range sometimes is all of the numbers, and sometimes, especially when we have just even power produce positive numbers, then the output, the range will be positive. We can see above the x-axis, above the x-axis. Okay, what is also important? One of the important things, yes, is end behavior. How these monomials or later polynomials behaves, how function behaves, how y behaves as x approaches positive infinity or negative infinity. Okay? That's we have to know, and this is the notation. Like we will check as x is approaching, yes, that's the positive infinity. Then y, what is y doing? And then as x is approaching negative infinity, we know the symbol, y is doing this. Okay, let's just maybe look at the function y equals to x squared. Okay, we will do x squared and x cubed. Okay, we know the graph. We know the graph and we can see as x is getting bigger and bigger, meaning that it's approaching positive infinity, I will square that big numbers. Yes, we will square it. That means definitely y will also approach positive infinity, because squaring positive number, we also getting positive number. Now, when x is approaching negative infinity, is going this way. What happened with the values like negative 10, negative 100, negative 1000? We will also square that number and the output will be also positive. Yes, as we can see, the squares, the end behavior, like will go up and up on both sides. And that means it's important to know the end behavior. That means this is actually, yes, this is the end behavior. Okay, let's take function x cubed, for instance. What is happening with the function as x goes to positive infinity, then function y, which is defined as a x cubed. We can think algebraically. Of course, infinity is not really like a number. Yes, that we cannot really involve infinity in arithmetic operations. However, in this situation, we can just think big numbers cube, positive big numbers cube will be positive. And we can nicely see x is getting bigger and bigger, and then y, the big values are cubed, then y is also positive infinity. As x goes to negative infinity, yes, then taking negative numbers to the power of odd number, we will get negative number. That's we can see negative x, negative like 2, it will be negative 8, for instance. Yes, negative 3 will be negative 27, because that means all negative numbers we can increase to the, I mean, theoretically we're decreasing, but x is getting to the negative, in the negative direction, negative infinity, then the y values are also getting negative infinity. Okay, that means the end behavior is really important. And what we can do now, we probably also remember from algebra class, when we have polynomial, always the leading term, in this situation we have just one term. This is the leading term, this is monomial. But this leading term will actually indicate the end behavior. Yes, algebraically we know that the other terms they don't have like impact on the end behavior. That's me. Let's see. We have the first exercise and we have to graph this function. We may recognize right away that it's a polynomial. It's a little bit different form, yeah? But this form is easier because we see the x-intercepts. That's me. Let's maybe, okay. First of all, what happened? We really have to know the degree, because if we will know the degree and the leading coefficient, we can predict, we can compute, we can state not really predict, we can get the end behavior. Let's see what's happened. What is the degree? We have x minus 1 to the power of 2. That means this will be x squared if we will end some other terms. Yes, I don't have to expand them. This one will be, yes, I don't know, but this will be negative x cubed, correct? Because it's negative. And then this is just x, and the rest of them, which is plus 3, and this is also x, because it's plus 2, just simple. That's now if we will multiply this, yes, we don't need other terms, we just need the leading. That means x squared, negative x cubed, x and x. When we multiply everything, it is positive x squared, negative x cubed, positive x, then the leading coefficient will be negative, and then x to the power of 2, 3, 1, and 1. When we multiplying, we adding exponent, 5, 6, 7, and then the rest of the terms. Am I right? 5, 6, 7. Okay. I mean, that's the leading function. I mean, leading term and leading coefficient. Okay. That's now. Let's look at this end behavior. We have x to the power of 7, and we have to also include that arithmetic. Sx, yes, let's see, Sx goes to positive infinity. Yeah? We may do algebraically. We may imagine that x is positive big number. Positive big number to the power of 7, it's still positive big number. With that negative, it will be negative big number. Okay, we got it. As x goes to negative infinity, then we can imagine that negative big number is raised to the power of 7. It will become negative big number. With this negative coefficient, it will become positive. That's what we know. Let's use the xy plane. As x is positive infinity, function will actually go down. See, negative. And then as x is going to the negative infinity, function will go up. That's we have the end behaviors up and down. I don't know, we have to think how function looks like, because it's just this possibility, but let's see. Now, actually, I draw something. I don't know if this is correct. As I said, the easiest function. What we need this x-intercept. Wherever is the x-intercept, function will intersect the x-axis. But we also know the rule, if it's degree higher. Okay, that's what we see. From the first factor, we have to figure out where this function is 0. That means this function is 0 if this, let me rewrite for you. When x minus 1 squared is 0, or 2 minus x cubed is 0, when x plus 3 is 0, and x plus 2 is 0. Okay, that means from the first one, we have 1, x equals to 1, x equals to 2, x equals to -3, and x equals to -2. That's the x-intercept. Okay, let's do a little bit bigger. Okay, I mean I can put -3, -2, 1, and 2. And we know that we're starting from below the x-axis. Now, at each x-intercept function, we have to intersect. However, if the x-intercept is a multiplicity of 2 of the even number like this one, we will not intersect, because we can think we intersecting and then we coming back. Yes, that's we kind of like at 1. We intersecting and coming back, but we cannot go above. That's mean what we know, that if the x-intercept came from the even power, 2, 4, 6, and so on, then we just touching the x-axis, below or above, depends where we are, okay? When the x-intercept came from the even odd multiplicity, then we can simply intersect, but we remember cube will make the function a little bit flatter at that point. And then that's the single one, -3 and -2, then we have no problem, we can just simply intersect. Okay, that's it. Let's start from the below, because we know the end behavior. At 2, we will intersect, no problem, but we will make a little bit flat. We can see like x cubed. At 1, now we have to go to 1. At 1, we actually bouncing because this is even. Okay, then at -2, we will just intersect, okay? And at -3, we will intersect. Perfect. Okay, and end behavior is correct. Function goes up here and function goes down at positive infinity. One thing what is maybe also important, the y-intercept. Yes, y-intercept. Because I don't know, this is just like just the really, really rough graph. And also I don't know how high the function will go. Yes, but this is definitely a good draft of the function. But let's maybe find the y-intercept. Y-intercept, we may get it if x is 0, right? That means if x is 0, we may remove x, and then what we will have? Y as x is 0, we will have -1 squared times 2 times 2 cubed, we can see, and then times 3 times 2. Okay, -8 times 6, -48. Wow, a little bit higher. I suppose to draw it, but it's fine. Okay, it's perfectly fine. Okay, that's really important to know, because now let's look at this. I can possibly erase this because we have this on the video. One thing that I really want you to know how to grab this, for instance, in calculus class, I can give you something like this, the polynomial inequality, for instance. That's we will have this, and I will ask, please tell me where this expression is greater than or equals to 0. For instance, something like this. Let's see now what you will do. You will follow the same process that I just did. You will graph the function and you will check where this graph is above the x-axis. Because if the graph is above the x-axis, this expression, this multiplication will be always positive. And we can see above the x-axis is here. Yes, it's actually here. Okay, and is here. That means all of those numbers, all of those. And since we have equals to, we may combine these two intervals. That means x belongs to, that's also important notation, x belongs to, okay, from negative infinity to -3, we may use brackets because we including this endpoint union from -2, and I can say from 1 and from 1 to 2, but I can combine these together because we including zeros, because at 1 the function is 0, but 0 is still good. Okay, that's we can see how nice it is to get this inequality solved. This is the reason. Okay, okay, that's me know everything what is in exercise 1. Now, let's look at quickly rational functions, okay? Because that's the basic functions, Okay, rational function is actually the quotient of two polynomials. That's now when we take one polynomial, two polynomials, making a ratio, yes, the ratio of two polynomials, the quotient of two polynomials, we're creating a rational function. Now, rational function, domain of the rational function, it will be not all of the real numbers like polynomials, because we want the polynomial from the denominator not to get 0, the value 0. That's we have to eliminate its x-intercepts. Yes, we will not accept them. And usually, not always, yes, we will also look at them. Usually we will, the numbers that are not in the domain, we will have an asymptote, or we may have also a different behavior, but we will weigh this later for calculus. Okay? Remember, we can have an asymptote or we can have a whole. Yes, we can have different situations. Now, when we will, because in general, algebraic function, yes, is they will result in the sum, the difference, product, quotient of all of the algebraic operations. Yes, like root function. That's when we see the root function, we can call algebraic function. When we see something like this, the expression taken to the power of any number, basically, not even the positive integer, we can call algebraic function. Actually, negative will create a fraction. Fraction will be the rational function. And then when we have a ratio not exactly of the polynomials, but any other like algebraic like expressions, we will call algebraic function. Okay? That's we don't know, they are not basic, they are not elementary. That's mean this one, we really need some calculus 1 analysis to get the graphs. Okay? Not thinking, of course, about the graphic calculator or any graphing equipment, okay? But the basic function, we can draw it. That means, for instance, again, just talking really briefly about the type of the function. Okay, let's mean now, when we have this nice rational function, because this is the ratio of two polynomials, just the linear polynomials, yes, let's see if we can graph. Because let's maybe start with 1 over x. Yes, 1 over x is the basic, actually elementary, section 1.1, rational function, the easiest rational function. And this is hyperbola in the first, the third quadrant. Now, we also know some like transformation. When I put negative in front of the function, I will flip. We will do the reflection about the x-axis. Yes, when we put the x just in front of the x, each x in the formula, which this will result in the same, we will flip around, we will do the reflection about the y-axis, and so on. When we add number, we will shift up. When we add number to the x, we will shift left, and so on. Okay, that's we have to know all of the basic transformation, and that's what I'm gonna use to get that graph. I mean, first of all, we will see, I would like to see x plus 5 minus 6, x plus 5. Okay, you probably see what I did. I added 5, but 5 minus 6 is still negative 1. But now we will have x plus 5 over x plus 5, which is 1, and then negative 6 over x plus 5. Then we have 1, as we can see, we will lift everything by 1 unit, and then minus, multiply by the 6, the purple function, and then we adding a number to x plus 5, we will shift 5 units to the left, or actually to the left. Yes, when we adding, we're shifting to the left. Okay, that's let's see what we can do. X plus 5, and actually 5 is not in the domain, correct? 5 is not in the domain, and we know in this situation it will be a vertical asymptote, negative 5. I mean negative 5 is not in the domain. Okay, now we're shifting the entire function 1 unit up. This will be a horizontal asymptote because we can see these asymptotes are 0 and 0. Now we have negative 5 and 1. Still the same like templates, the same shape, hyperbola. But since we have negative, we will flip. I will not draw it in the first quadrant and the third quadrant, which is shifted. No, that's wrong. Because we have negative, we will draw in the second and fourth one, if I can say this way. They are still shifted by these asymptotes, okay? Vertical and horizontal. Now we can also find x-intercept and the y-intercept. X-intercept we can see, I can maybe draw this, function equals to 0 if the numerator equals to 0, 1. X equals to 1, x-intercept. My pen is not following what I'm really writing. Okay, now how we can get y-intercept? We have to just find the value of y when x is 0. That means 0 minus 1, 0 plus 5. Negative 1/5. Let's keep it this way. That's negative 1/5. Don't worry for the scale. When the labels are correct, everything is correct. Labels, y and x. Okay, beautiful graph of the rational function. Basic rational function. But what I didn't use any calculus, of course. I just used the transformation. I just used the algebra information. Okay, also make sure because it's important. Okay, let's keep moving. Okay, transcendental function. I will not talk about this a lot because we do have like separate sections, 1.4, 1.5, 1.6. But just for your information, they are not algebraic. Yes, they defined totally different. X is in the exponent, A is base, A is always positive, never 1, because 1 to the power of any number will be 1. Constant function, that will be not really challenge. Okay, yes, that means we have to have it in the definition. And domain are all of the numbers. That means this is if the base is greater than 1, function looks like this. If the base is less than 1, function is decreasing. So I mean, that's the exponential, and logarithmic are the inverse to exponential. Okay, let's look, just scan the graphs, and we will talk about this later. And also we have beautiful trigonometric functions. Sine of x, actually I have sine of t. Sine of t, cosine of t, tangent of x, cotangent of x, cosecant and secant. Okay, that's when we really have to know the graphs because they will be important to analyze some calculus. Yes, calculus analysis. Okay, and then we have inverse trigonometric functions, inverse sine, which we actually can call arc sine of x. And then arc cos. Oh yeah, we have arc sine. Okay, I have it. I didn't, because we may use the inverse notation, yes, but we just alternating. Okay, arc sine, arc cosine, and arc tangent. We will also talk about this later. One thing that we may do on this slide, let's find the end behavior of arc tangent of x, because we can see this function is defined. That means for arc tangent of x, as x goes to positive infinity, what is happening with the function? As we can see, x is increasing, and the values, the corresponding values, are not getting like really high. They not go to the infinity. They are limited. They are bounded by value pi over 2. Okay, and then as x goes to negative infinity, okay, values are limited by negative pi over 2. That means it's quite helpful to know, because we will use this a lot. Okay, the end behavior of arctangent of x. Okay, and we will call it soon, yeah, next week. We will call it really soon a little bit different, yes? We will use the basic concept of calculus, which are the limits. I don't want to uncover the mystery, but yes, we will use a little bit different notation, but it still will be the same concept, the same idea. Okay, what next? Some linear combinations, which I think I mentioned a couple of times. We may add functions, subtract, multiply, divide, always thinking that denominator cannot be 0. And then we have a linear combination of these functions, which we will call algebraic function. Okay. And we can also do one important operation. Let's look at this composition of two functions, yes? Or compound, we can call compound function. That means this notation indicates that function f is compound with function g of x, and meaning that f is the outer function and g is the inner function. That's also important to identify f and g. Okay? For the domain, we have to respect domain of the function f and domain of the function g. And then whatever new formula will arrive, then we also have to look at the domain. You can also check for the section 1.3, I have a short video about the domains, how to find the domain of the function. Please also check this. Okay, now really quick exercise. When we take these two functions, x squared and sine of x, what is the composition? Function f is the outer function, that means x squared. Instead of x, we will put sine of x, sine square of x. Yeah, that's what I mean. Looking at sine square of x, I want you to identify which one is inner, which one is outer. That means the inner function is sine of x, and the outer is the power squared, quantity squared. Okay, square root of x and 5x cubed. When we say the square root, yes, square root is the outer function, we can just put square root of the function g of x, 5x cubed. Okay? Now one more, tangent of x and 1 over x. When we combine f and g, f, tangent of x, is the outer function. Instead of x, we will replace x with 1 over x, tangent of 1 over x. And actually, it's interesting when we will do composition g, compound with f. Function g will be the outer function. That means 1 over x, and instead of x, we will put f of x. F of x is tangent, and 1 over tangent, we all know, is cotangent. Interesting, yes? From this, we got cotangent. As in, cotangent is also like a composition of two functions, if we would like to look at it this way. Okay, we good with this? Now, let's just draw a couple of functions, and then we will be done with the basic class of functions. But I want you to really know how to draw polynomials, rational function, and the piecewise defined function. Oh, too many inequality sign. Okay, Let's draw, yes, absolute value of x. Everybody knows how absolute value of x looks like. We can draw function x, or maybe I can use x, but we can only take, yes, x, the positive, only if x is positive. That means starting from 0, because including 0 and this, we can only take this. And we can draw negative x. Negative x looks like this. Yes, this is negative x. This is positive x. But we can only take negative if x is negative. That's mean on this side. And we all remember the V shape. This is the absolute value of x. We're not taking that green parts. That's where the function comes from. Okay, for instance, another one, x plus 1 and 1. X plus 1 is defined because we can draw the entire function. X plus 1. X plus 1 looks like this. Y-intercept 1. X-intercept negative 1. We know how to calculate this, but we can only take for the positive x's. That means this is 1 and equals to, that means I will put the solid dot. Oh, it's a little bit wavy. Okay, and then 1, the constant function 1 looks like this, and we can only accept when x is negative, because we cannot have, okay, that's the red graph is the graph of the above function. We're not looking at the green parts, okay? That's how you can draw a piecewise defined function. Excellent, and now this one, oh, a little bit, also elementary function, functions, elementary functions. Okay, let's draw x squared. Let's start with that. We know x squared, parabola x squared, beautiful. And then square root of x, like this. Oh, they intersect. Would be nice to find that number. Of course, this is 0. I mean, this one is square root of x, this one is x squared. Okay, where is 4? I will assume that 4 is somewhere, let me put here, 4. Okay, that means x squared is defined for all of the x's less than 4. That means, I have to go a little bit too big. What do you think? Of course. No, let me try if no. Let's do smaller, because 4, we know what is x squared. I mean 4 squared. Let's do it here. Okay, xy, because everything is parabola and square root. Again, a little bit too big, but at least we have room now. Okay, we may probably guess that value, but we will calculate. This is 0. And then I believe 4 is somewhere here. That means I can start drawing square root of x for all of the x's greater or equals to 4. That means this will be that part. We're not taking the green one. And I have to stop parabola at this point. Right? That means we will take that part and this one. And it's open because x squared is defined for all of the x's less than 4, not equals to 4. This is open, this is solid because we cannot have. Okay, the red graph is the graph of the function f of x. But just to know how to find this, yes, we will call points of intersection. I can say that x squared must be equal to square root of x. We can see they are equal for 0 and for 1, yes? But algebraically, we can square both sides. Then I can subtract x from both sides. We can factor out x cubed minus 1, and then x equals to 0, or x cubed minus 1 equals to 0. 0, and 1. Okay, that's how we can find points of intersection. Beautiful. Okay, and then the last exercise is this one. Really quickly, I hope really quickly, we can draw this, and I can, yeah, all of these pieces are the elementary function. That's we have to know how to draw them. Okay, x squared, we have no problem. Line with the negative slope, we have no problem. Constant line, no problem. 1/2 x minus 1 is the line with small slope 1/2. And this one is function x cubed. That means first of all, we have to, not x cubed, cube root of x. Could be rewrite as x to the 1/3. That's we can see cube root of x, and we know how cube root of x looks like from section 1.1. Looks like this. It's the inverse to x cubed, a little bit flatter, and 0. Okay, that means this is 0, 0. Now, when we subtract 2 from x, means that we're moving 2 units to the right, and we adding 2 to the entire function, then we will put 2 units up. Okay, that means 2, 2, okay? Just basically that red dot, which now will become green, has to be shifted. That means the graph will look like this. Okay, that means this is the graph. But now let's put everything together. I don't know exactly how to plan it. Let's look at this way. Okay, that's we have parabola x squared, but we have to stop at -2. Correct? We have to stop at -2. That's maybe we will do, at -2, not at +2. Okay, let me actually draw the parabola. Now, if we will draw the line, -2x plus 3, that means it's negative slope, x-intercept is, let's just do it, x-intercept is 3. Because what I want that point of intersection. That's really quickly, point of intersection, and we will take x squared, not x cubed, because we were just talking. Let's do x squared must be equal to the line -2x plus 3. X squared plus 2x minus 3 equals to 0. And then we may factor out. I believe this will be plus. That's we have x equals to 1 or x equals to -3. Beautiful. That means this is 1. Okay. I don't know if we need this, but maybe. And the other one will be -3. Yes, when we will intersect, it will be -3. Okay, that's we have line. Let's maybe draw all of them. Then 5 is just, actually 5 equals to 1. That means I can maybe do it right away. It will be just a solid dot. I don't have to draw a horizontal line. I will make less mess. Okay, but x squared is just from -2, and -2 squared is 4. That means we will stop there. This is x squared, okay? Now, that means from that point, from the -2, we have to find out the line. Line is from -2 to 1, okay? And with this will be open. That means line is from here to here. What is the value from -2? -2 times -2 is 4 plus 3 is 7. This is 7, okay? Okay, that's the red, okay? The red graph is the graph of the piecewise defined function. Then it's a solid dot. This is open. This is open, this is solid. We cannot have two. We know we just started this is open. Okay, I can keep it open. Now, that we have line, we have parabola, and we have 5 constant. Now that's beautiful. We know we need 2. I can draw it like this. but it's only from 1 and it's open. Okay, from 1, this value is 2, 2 to 10. When we put, and the 10 will be, what's the value? 10 minus 2 to the power of 1/3 plus 2. Yes, we're looking for the value. 8 to the power of 1/3, which is cube root of 8 plus 2. 2 plus 2, 4. Okay, that means this is 4. Beautiful. And now we need the line. When we put the line, that means this is this. When I put 10 minus 2, just checking the value, will be 5 actually. It's also 4. That's we starting drawing a line. The line actually is like this, but we only need from that point. That means we will get this. Beautiful. And we don't have to. That means all of the red parts. Okay, one more time. Parabola, then line, dot, just for the constant, and then cube root function, cube root, 2, 2. Yes, we shifted, and the line with the slope 1/2. Okay, let's make sure that you know the graph because we will analyze this later from the calculus point of view. Okay, now you are really good with the basic, basic functions. I mean elementary functions section 1.1 and just basic class of function. Okay, thank you.